To understand the concept of derivatives, the slope of a curve needs to be clearly understood as they interlink with each other. A slope can be defined as the rate of change between y and x, or interpreted as delta y over delta x. If we have the points 4 and 8 on the y-coordinate and 2 and 4 on the x-coordinate, we can calculate the slope. The change in y is 8 minus 4, and the change in x is 4 minus 2. Therefore, the slope is 2, or in other words, the rate of change is 2. However, not all slopes have a constant rate of change. For example, f of x equals to x squared. This is where the limit comes into place, where it involves a tangent, where a tangent can be defined as a straight line or plane that touches a curve at a point. As you can see from this example of fx equals to x squared, the tangent and the secant line are really close to each other to know the exact slope at the instantaneous point along the curve. Therefore, to find the tangent, you need to find the limit of the value as h approaches. Therefore, the definition of the derivative is f of x plus h minus f of x over h. For example, if the function of f of x is equal to x squared, what is the derivative at x is equal to 2? Using the definition of derivative, we get this. Now we can solve this equation. And thus, as x tends to 0, the derivative of the function of f of 2 is equal to 4.
An example for derivatives in physics is to find the derivative of d equals t squared plus 5t plus 6 at t equals 4, where the distance is in meters and time is in seconds. For d equals t squared plus 5t plus 6, the derivative of d equals 2t plus 5. At t equals 4, the derivative of d equals 2 times 4 plus 5 equals 13. To find the unit, we know that the derivative is a slope at any point. Since we know that the slope of the graph equals change in d over change in t, we can determine that its unit is in meters per second. Therefore, the derivative of d at t equals 4 is 13 meters per second. Looking at this result, we can determine that the derivative of a dt graph is the velocity of an object. We can find the derivatives of functions easily through the use of some rules, such as the power rule, where x to the power of n equals n times x to the power of n minus 1. The sum rule, where f plus g equals derivative of f plus derivative of j. The product rule, where f times j equals derivative of f times j plus derivative of j plus f. Quotient rule, where f over j equals derivative of f times j minus derivative of j times f over j to the power of 2. Also, the derivative of a constant equals 0. We can also use a combination of these rules to find the derivatives, making it a very powerful and useful tool in finding the derivative of more complex functions.
Let's say we have a function f and we find the derivative of f like so. If we then find the derivative of this, we have found the derivative of f, which can be rewritten like this. We can call this derivative of f the second derivative. But what exactly is the second derivative? We previously learned that the derivative is the rate of change, so the derivative of the rate of change is just the rate of change of the rate of change. There are several uses for the second derivative, one of which is the mathematical optimization, which is where we are trying to find the input that is required to get the best output, or the most extreme output. This is useful in situations where you wish to find an extreme for a function. For example, in chemistry, the free energy in conformational isomers can be calculated and given as a function, and using the second derivative test, its extrema can be calculated. By finding the absolute extrema, which in this case is quite feasible as a result of the small range of possible values, we can find what conformation of isomers is most stable. This is where the energy is lowest and therefore is its absolute or global minimum. We can also find the conformation of isomer where it is the least stable or most reactive by finding the global maximum, which is here. This allows us to find what conformation is needed to keep the isomer as it is, or what conformation is needed to interconvert it to another isomer at the most efficient rate.